algorithms to quantify microstructure and fracture in metals. My name is Ravikiran Yalla. I am an assistant professor in civil and environmental engineering at North Dakota State University. Steel is the most popularly used engineering metal in the world. Despite the pandemic, about 1.6 billion tons of crude steel is produced globally in the year 2020 alone. Now I'm going to give you a fun statistic about how much steel we consume in the developed world. Let's look at the top three economies. In the US, every person, or on an average, a person consumes around 63 kgs of meat every year, whereas they consume around 330 kgs of steel every year. So when we consider China, we have 13 times more consumption of steel when compared to meat. And that ratio is only going to increase when we look at the Japan, which is the third largest economy. So definitely we are not putting steel on our plates, but it is being consumed. So where is the steel going to? Let's look at the fourth largest economy in the world, Germany, to see where exactly the steel goes. About 31% of steel in Germany is used for construction purposes. And the second largest consumer of steel is automotive industry, where 26% of steel is consumed. Why are we so much obsessed with this structural steel? Steel is quite inexpensive, abundantly available in the Earth's crust, and it has high strength to weight ratio. And besides all these good properties, steel can be tailored according to the specific engineering needs. So let's concentrate on the top two uses of structural steels and the steels that are used in these two top applications, namely structural engineering or civil engineering or transportation engineering and the automobile industry. Here I have presented the microstructures of two steels. Towards the left, you can see the ASTM A36 steel, and towards the right, you can see the quenched and partitioned 980 steel that is developed for use in automobile applications. So if you look at the ASTM A36 steel, you can see two phases. The lighter phase is the ferrite phase, and the darker phase, which is nothing but ferrite, which is referred to as perlite, which is nothing but ferrite plus Fe3C, are the two phases. Here, in the case of QP980, we have martensite, we have ferrite, and we also have retained austenite. In the case of ASTM A36, ferrite is a phase that imparts the ductility to the steel, whereas perlite is the harder phase which gives strength to ASTM A36. Remember that strength and ductility are antagonistic properties. Just because perlite is more harder, it is going to have less ductility. In the case of QP980, ferrite is once again the player when it comes to ductility. Martensite imparts a lot of strength. Retained austenite, when it deforms, becomes martensite, thereby increasing the strength as the deformation increases. So there is a striking difference between the structural engineering steels and the steels that are used in automobile industry. About 95% of the structural steel used in the United States is recycled from scrap steel, whereas the steels that are used in automobile industry are manufactured with better quality control. When it comes to the strength of structural steels, the average strength is around 500 megapascals. But when we look at the strength in the case of QP980 steel, it is around 900 to 1100 megapascals. This is quite understandable because in the case of automobiles, we want the weight to be as low as possible. Because if you can reduce the weight of an automobile by 10%, the fuel efficiency goes up by 7%. So one thing is common between structural steels and automobile steels. No matter their differences in their strength, they get their strength depending upon the microstructure. Of course, I do understand that there are some people who work at the nanoscale who would like to relate the strength of a metal to the dislocations. But I am somebody who lives in the microscale. So let me focus mostly on what happens at the microscale. So is strength the only property that depends upon the microstructure? May not be the case. So now let's look at the fractographs, which are nothing but microscale images of fractured images of microscale images of fractured surfaces. So here I have three different types of fractures that are very common in steels. The first one is intergranular fracture. When a steel experiences intergranular fracture, if you look at the fractured surfaces at the microscale, you should be able to see the exposed grain structures there. And the second most popular type of fracture in steels is the ductile fracture, where when you look at the microscale, you can clearly see the microscopic cup and cones. And the third one is the transgranular fracture, where we could see at the microscale river-like patterns. And this is called transgranular fracture or cleavage fracture. So intergranular fracture is very common in tool steels, where you have high carbon content and a high amount of defects. When it comes to the ductile fracture, both the ductile fracture and transgranular fracture or cleavage fracture is very popular in both the structural steels and automobile steels. When it comes to structural steels, the ductility ranges between 21 to 40%, and in the automobile industry, ductility is around 12 to 18%. Ductility is something which is decided by both the industries, but only structural engineering industry can afford to have the ductility, because high ductility means low strength. So why do we need more amount of ductility in structural steels? If we don't have enough amount of ductility in structural steels, whenever there is a huge earthquake, there is a good possibility for collapse, leading to catastrophic events. In automobile steels, yes, of course, once in a while there could be a crash. But if an automobile crashes, the probability that that particular accident will lead to a huge catastrophe is low when compared to a structure. So we just live with 12 to 18% of ductility in automobile steels. Of course, fracture depends upon many things other than the microstructure, which are the presence of defects, the existing macroscopic stress state, and the preloading conditions to which the metal has been subjected. But one thing is for sure, both the strength and ductility of steels have microscopic origins. So if you want to understand, if you want to develop fundamental understanding of fracture and strength of metals, we may have to look at the microscale. Keeping this fundamental need in mind, most of the scanning electron microscopy manufacturers have ramped up their production, and they have come up with some of the most amazing scanning electron microscopes. For instance, the ZEUS multi-SEM is the world's fastest scanning electron microscope. It has 91 parallel electron beams to capture images. It is so fast that it could capture 1 square centimeter sample at 4 nanometers pixel size within less than 3 hours. So that means you will be sitting on millions of SEM images and fractographs in a very short period of time. That's good and bad at the same time. It's good for the obvious reasons. It's bad because if you just rely on the manual interpretation, it is going to take forever to interpret whatever is given by these modern SEMs. Manual interpretation is very slow, very laborious, expensive, because you have to hire a scientist to get this done. And besides all these, it is very subjective in nature. So if you want to catch up with the advancements in the microscopy world, we have to rely on automation. So in this particular talk, I would like to focus on two specific problems. The first problem is about characterizing the microstructure. And the second problem is about characterizing a fracture surface. To the left, you have two types of microstructures. One is the ferrite perlite microstructure, and the other one is ferrite martensite microstructure. Both those two microstructures are possible in structural steels depending upon the thermomechanical route to which the steel has been subjected. And in the problem 2, towards your right, you can see two fractographs. In one fractograph, you can see a brittle fracture or a cleavage fracture or a fracture dominant kind of a fracture here, and some ductile fracture here. And the second image, or the image that is towards your extreme right, has a ductile fracture dominant fracture. So we would like to characterize these microstructure and also the fractures from the images that were obtained from microscopes. So please remember that these images are taken from scanning electron microscope, while these images are taken from a digital optical microscope. So the goal here is for the problem 1 to identify distinct phases and evaluate their corresponding volume fractions. And in the problem 2, we would like to identify the brittle and ductile fractures in the metals and quantify their area fractions. So on the periphery, this might look like a very simple problem, which actually isn't the case. Why? Because most of the existing softwares, commercially available softwares, rely on pixel intensity to identify the various metallurgical phases and also the types of fractures on a particular SEM image. But the problem here is, here we have ferrite perlite and ferrite martensite microstructures. If you just simply plot their pixel intensities, and if we label each of the pixel manually and plot their pixel intensities, you can clearly see that there is a huge overlap between perlite and martensite and between martensite and ferrite. So if you just simply use the pixel intensities in conjunction with some kind of a clustering algorithm, there is a huge probability that you will end up with a lot of misclassifications. On the other hand, in the problem 2, this is slightly more complex, just because not only both the two fractures have similar kinds of pixel intensities, in addition to that, both of them have some kind of striations. In this case, these striations are like wavy striations, and here the striations have cup and cone shapes. They have the same grayscale too. So we have to make sure that whatever method we would use doesn't depend upon the pixel intensity alone. So like we could also argue that we could use shape and color as the features to identify the phases. But as we have already seen here, most of the phases and the types of fractures have similar kinds of colors. And we cannot also rely on the shape just because they don't have any specific shape. Here, the ductile fracture and brittle fracture doesn't have any specific shape. Here, none of these phases have any specific shape, so we can't even rely on the shape. So in this particular study, we thought of relying on the texture. So texture is a different kind of concept because shape and color are perceived more or less the same way by both computer and by a human being. But texture is perceived in a slightly different way. For a computer, the texture could be a repetitive pattern or a non-repetitive pattern, but it is a distinctive pattern, distinctive enough to recognize. Whenever I say distinctive, how does the computer distinguish one type of texture from other type of texture? There are 3 broad approaches. The first approach is the statistical approach, where we investigate the distribution of the pixel intensities one with respect to others in a certain neighborhood. And in the structural approach, we try to find the most common, basic, repetitive element which forms the entire structure or the texture. And in the third approach, which is the transform models, we use some kind of mathematical models to transform the given texture into something else that is more distinguishable when compared to existing textures. So if this is such an important problem, somebody in the past should have solved it. Yes, of course, there were few people in the past who tried to address this problem. So 2 different approaches were used. The first one is a threshold-based technique in which they had some threshold value above which they considered they had a certain type of phase, below which they considered that they had another kind of phase. So 3 sets of researchers have attempted to do that between 2009 and 2014. Some of them also used existing commercially available softwares. So the second approach is the deep learning approach. The deep learning approach is definitely a much better approach to use. But the problem with the deep learning approach is we need large quantity of data, large number of data images. And it also costs us a lot of computational time during the training process of the deep learning algorithms. So To circumvent these two problems, which is if you just simply use the pixel intensity, it's not going to work. And if you use deep learning algorithms, it is going to cost us a lot of time. So if you have 1 million images and if 1 minute is consumed for each image, assume that you will not get the results until 1 million minutes, which is still expensive. So we have to have some simple approach to kind of characterize the metallurgical phases and also identify the different fracture mechanisms based on microscopy analysis. So what we thought was we wanted to use machine learning approach. And in the case of machine learning approach, we need features and a machine learning algorithm. Features are the one which dictate the outcome of an observation. In this case, whether it is going to be a certain phase or a certain type of fracture. So for evaluating the features for the microstructure problem, we used gray level co-occurrence matrix. So this gray level co-occurrence matrix is a concept that was proposed by Harlick et al. In the year 1973. It is a very old but forgotten in the field of microstructure analysis. We brought that back. So here we had a simple image which had 7 grayscale levels. So what we have done is, for the sake of saving more amount of computational time, we used quantization techniques to even reduce it to 4 grayscale levels. Quantization is nothing but just a binning technique. So here you would have numbers ranging from 1 to 4. So in this particular approach, what we'll do is, if you want to find this particular element in the gray level co-occurrence matrix, which has size similar to the number of gray level scales that are available in a particular image, we measure how many number of times. Say for instance, if you're looking at the 2-2 element, we evaluate how many 2-2 values are there in the diagonals in the entire quantized image. In this particular case, we had 1, 2, 3, 4, 5, 6 number of 2-2 combinations, ij pixel intensity values, and thereby we have 6 here. By repeating this exercise for all the values here, we get all the values within the GLCM matrix. So once we have this matrix, we evaluated 20 features, including homogeneity, contrast, energy, entropy, and so on and so forth. Some of them have some physical meaning, most of them don't. That is the difference between how we as human beings perceive texture and how computers perceive a texture. Human beings have whatever we see has physical meaning, but whatever computers see has only mathematical meaning. So what we have done is we took several images of the microstructure and we generated a training data set with 735 observations. And in those training data, from those training images, we were able to generate features for varying sizes of the images. And then we used this data to train 4 different machine learning algorithms, namely naive-Bayes, k-nearest neighbor algorithm, linear discriminant analysis, and decision tree. And on the other hand, we also generated test data, and we used this test data to evaluate the efficiency of the training process. So here, I would like to emphasize the importance of features that we have chosen to work with. Although this is not fair, I would like to make a comparison between how our method fares with comparison to in commercial software, which is ImageJ. In the case of ImageJ, if you want to use it for identifying the phases using an optical microscopy image, you have to specify well in advance how many phases are readily available in that particular microstructure. So if you just put 2 as the number of metallurgical phases, then this is the image that you get. And if you put 5 as the input, then this is the image that you get. That means these are the 5 phases that are available. In our approach, you need not specify the number of phases. It will automatically identify what will be the number of phases. So this will also reduce the amount of manual intervention necessary for getting the job done. So 100% automation is possible. So here, if you just simply live with the intensity, pixel intensity, this is the kind of image that you get. The white one is the ferrite, the dark one is the perlite, and you see all this pink one, which is martensite. We don't have any martensite in this particular image, but still it shows up because we just simply chose to work with one feature. Instead, if you choose intensity, pixel intensity plus top 4 features, this is the image that you get. If you add one more feature, you get a very clean image in which the grain boundaries are also not misread as a new face. So the amount of martensite in this figure is very low. It is negligible. At the same time, you don't need to specify anything to the software. When you use it, it will automatically figure out the number of phases in that particular microstructure. So we wanted to see how well this is going to perform in various scenarios. We looked at the ASTM A36 steel that is heated until 500 degrees centigrade, cooled to room temperature, because that produces a certain kind of microstructure, which we see here. And we used all the 4 classifiers to identify what are the phases. And strikingly, we were able to achieve very good accuracy in all these cases. We also looked at the ASTM A36 steel subjected to 900 degrees centigrade and water cooled, because it will generate martensite ferrite kind of microstructure. And when we used all the 4 classifiers, once again, there is no difference between what we observed manually and what we got from the machine learning classifiers. So when we came to the fracture problem, there are 2 unique problems associated with this, in addition to the problems that we solved for the microstructure characterization problem. So in the case of fracture surfaces, we don't polish the surface, we use the fracture surface as it is. So there is a good scope for variation in the illumination condition from one spot to the another spot, creating huge confusion to the computer intelligence. So we have to somehow make use of an algorithm which is grayscale invariant. And the other thing is, if you see in one specific orientation, this image will have one kind of appearance of the ductile fracture, and if you rotate it, the same feature will appear, but it will be appearing in a rotated state. So we have to be very careful about how well we account for these rotation invariants. So in the literature, once again, they used multi-level thresholding, which is very basic. And also they looked at texture-based approaches, but the problem is they used GLCM and the advanced GLCM approaches. Once again, the GLCM is not scale invariant, and it is definitely not illumination invariant. So we wanted to look for a algorithm which is grayscale invariant and also rotational invariant, and we went with the local binary pattern. Local binary pattern is such a wonderful textural measure. So in the local binary pattern, we choose a particular window and we threshold out the illuminations in all the neighboring pixels with respect to the grayscale level of the central pixel. If the pixel intensity in this particular image is greater than this pixel intensity of this image, then we clearly know that this is going to be +1. If it is less, it is going to be 0. Thereby, you will be generating a nice binary pattern around the central pixel. You can choose the size of this window to be anything, but we only concentrate on the peripheral pixels. When once such a code has been generated, binary code has been generated, you'll just simply expand it and write it as a binary number. So here we started off with 0, which is below the GC, and then we went anti-clockwise. So it became 0, 1, 0, 0, 1, 1, 0, 1. And we can convert it into a pattern by multiplying each of these digits with 2 raised to n, where n is nothing but the position of each of these digits. In this particular case, this pattern turns out to be 178. Just because we are finding the relative brightnesses or darknesses of the surrounding pixels with respect to the central pixel, this is going to be grayscale invariant. That means if at all there is a pit on the fracture surface, somehow if it is dark, just because it doesn't receive the electron beam the same way other parts of the fracture surface is receiving, you still need not worry, because this local arrangement which thresholds with respect to the central pixel will take care of that grayscale. But the problem with this approach is, if you start with the 0 below the GC, you have one kind of a pattern. If you start with 0 above GC, then you'll have another kind of pattern. There is a possibility that you would have around 18 patterns. So the uniqueness is missing, and this is not rotational invariant. So how could we make this rotational invariant? We could use this we can make this rotational invariant by coming up with an uniformity measure. So if we look at the linear binary pattern that I just described, there are 1, 2, 3, 4, and 5 transitions from 0 to 1 and 1 to 0. So if we list all the patterns that are possible, we would get 36 patterns, out of which I listed only 18 here. So out of this 18, we have 9 unique nine unique patterns, out of which 8 are uniform patterns, and the ninth one is the non-uniform pattern. So if you have only one transition, there is only one transition from, sorry, two transitions from 0 to 1 and 1 to 0 here. So this is 2, and here also you have 0 to 1 and 1 to 0. You have two transitions here, and for all the uniform patterns you either have 0 transitions here, and here 0 and 8 had 0 transitions, and rest of them have 2 transitions. So these are referred to as uniform patterns. Any pattern which has more than 2 transitions will be referred to as non-uniform patterns. So this is a dark spot, this is a bright spot. These will characterize all the edges within the image. So once again, we use the same kind of setup even in this case, but we use linear discriminant analysis. And we looked at the histogram of uniform patterns that distinguish the ductile fracture from the brittle fracture. In the case of brittle fracture, we observed that the patterns, the uniform patterns that are corresponding to dark and bright spots showed up more prominently. And in the case of ductile fracture, we have seen the number of edges. So in the case of ductile fracture, we had more number of edges, and in the case of brittle fracture, we had more a number of dark and white spots. So we had 2 test images. The first test image was a brittle fracture dominant kind of a fracture surface, and the second one, towards the left, we had brittle fracture dominance, and towards the right, we had ductile fracture dominance. We have used a couple of approaches. One is the window approach, and the other one is pixel approach. In the window approach, we chose a window size, and we either classified it as ductile or brittle. And in the second case, we went every pixel, saw whether it is ductile or brittle, and we predicted the amount of brittle fracture surface and ductile fracture surface in both the 2 approaches. And in both the 2 approaches, the answers were pretty close to each other. So once again, this is one more test image that we previously discussed. And to conclude, in this lecture, I have discussed how we could use texture to our advantage to fully automate the metallurgical phase detection in structural steels that are subjected to various thermomechanical routes in order to produce a variety of microstructures. And I also discussed how we could use grayscale invariant and rotational invariant linear binary pattern in conjunction with machine learning algorithms to accurately identify the fracture type and to also understand the fundamental visual characteristics of fracture surfaces. So I would leave this presentation with a thought for all of you. The thought is more work has to be done to generalize this method to characterize the microstructures and to identify the fractures in a wide range of metals. I have known certain researchers who took this research from us, and they were able to generate more results in various amounts of various metals. So I hope that you will be able to do the same if you are looking for an automation solution. So this work has been sponsored by the North Dakota EPSCoR and also the NDSU Research and Creative Activity, and we thankfully acknowledge their financial contribution. Thank you.